Our next talk is entitled A Dependently Typed Calculus with Pattern Matching and Erasure Inference. This paper has been written by Matus Teschak, and he will tell us that erasure in well-typed programs is sound in that it commutes with reduction.
Hello, thank you for coming to my talk. My name is Matus Teschak and I would like to talk about erasure in dependently typed programming. Dependent types are great. They let us write specifications and formulate invariants and let the computer help us make sure that our programs conform to those specifications. For example, here's a program that reads a binary number from the input, adds 1 to it and prints the result out, where the type of binary numbers is indexed by its unary representation, which is easier to reason about, which allows us to give the function add1 a type that guarantees that add1 indeed computes the successor of the given binary number. Unfortunately, just by looking at the types, we can already tell that this program will run in exponential time and space with respect to the number of bits read from the input. Why is that? Well, if we look at the implicit arguments, which are usually hidden and filled in by the elaborator, we can see that each binary number also contains the unary representation of the binary numbers contained within, and the function add1 also takes a unary representation of the binary number it takes. And those unary representations are exponentially sized with respect to the number of bits, and therefore the representation of memory looks roughly like this. The useful bit on the left is dwarfed by the compile time only information on the right. So in this talk I would like to convince you that this is a real problem, that we should really address this, and that by specifying our programs more precisely we should not make them run slower, and we should not make a linear program run in exponential time or worse, just by saying about it that it calculates the right answer. I'll sketch that irrelevance, erased universes or laziness all solve a slightly different problem, so they are not always applicable or not always the best choice. I'll sketch the gist of how we can discover this compile time only information that might be too big, and automatically discover it and remove it from the program, thus recovering the intended runtime complexity. And I'll show this optimization makes other optimizations more powerful, and also makes the compiler run faster because there's less code to generate. In language like Coq, we might attempt to use the erased universe of prop. However, while this is great for erasing proofs, it's not so good at erasing indices, as illustrated by the function nat to bin. Because what should be the type of n? Should the type of n be erased or not erased? Since function nat to bin requires n to do its job, n must have a non-erased type. However, because the same n is used as an index of bin, it must have an erased type. So tying erasure to a type of a variable is not useful in this case. We might even try laziness, that works sometimes, but it's a dynamic fix for a static problem. We can already tell at compile time which bits can be erased and which bits we need for runtime. So we should not keep a runtime check to prevent evaluation of that information. We should just erase it altogether. Laziness is not an option in eagerly evaluated languages, and as illustrated by the function server loop, we have a choice here between accumulating thunks in the variable n if we do not evaluate it, and therefore leaking memory, or evaluating it and having n explode exponentially in size. Irrelevance can also be used to achieve erasure. However, irrelevance is too strong. By irrelevance, I mean the property of sub-expressions ignored in definitional equality. This is a very strong property, and it's not necessary for erasure at runtime. In Agda, irrelevance does not help us with the binary number example, just because it's too powerful and causes problems. Also, inference of irrelevance is harder than just inference of erasure. So if we just need erasure, we do not need irrelevance with all the consequences it brings. So what do we do then? Well, here's a small example. Function vlen that takes a vector and calculates its length. We can ask the question, can we erase the second argument of vlen called n? Or does vlen need to look at this argument to do its job? Well, in the first clause, the second argument is forced to 0, indicated by square brackets, because the vector is empty. So, since the types tell us that the second argument is 0, we need not look at it, we do not have to inspect it. In the second clause, the types tell us that the second argument is a successor of a certain number called n. So the types tell us the tag of the constructor, but they do not tell us what n is. However, on the right-hand side, n is used in the recursive call as a second argument of vlen. So if the recursive call does not need the second argument, we do not need n, and since we know the tag and we do not need the n, we do not need the second argument altogether, and it's consistent then to say that the second argument of vlen can be erased. To make this a little bit more formal, we need to get a bit more explicit about the pattern variables, so we insert the 2 lines starting with where that bind the pattern variables explicitly and give them types. Next, we number all colons and all applications in the whole program. So all name bindings are numbered now. Each of these numbers will eventually be replaced by a definite annotation R or E, retained or erased. But we cannot just fill in any annotations we like, because they need to satisfy some consistency constraints. So then we traverse the whole program and gather consistency constraints. For example, in this program we can notice that the annotation number 19 has to be the same as the annotation number 30, because it's the same function. It's the first argument of function vlen, so it has to have the same annotation. This is expressible in the horn clause form. Then on the right hand side we can observe that if s uses its first argument and vector length uses its second argument, then the pattern variable n needs to be available. This is also expressible in the horn clause form, and we can see it in the second line of the table. Finally, on the left hand side of this clause, we can observe that if n has to be available, then s needs to remember its argument, which means number 32 has to be retained, and vector length has to retain its second argument, which means number 31 has to be retained. This is also expressible as 2 horn clauses, and in this manner we go through the whole program, gather the constraints, and then find the solution with that erases as much as possible while being consistent with these constraints. This yields an annotated program where every variable and every application has been annotated with R or E, and the annotations are built into the type system. It's not something we keep on the side. It's really built into the type signatures. So then we can erase everything that's annotated with E, obtaining the program that we actually want to run, and that does not contain any traces of overhead caused by dependent typing and indices. This erasure system has some nice properties. For example, the function subst does not retain its proof argument, so the proof can be erased despite being matched on. The types tell us what the constructor tag must be. We know it's because there's only one constructor in the type family, and the argument x is not used on the right hand side. Therefore the proof can be erased and subst becomes an identity function after erasure. Of course, this is doable only if the type system is sound and does not allow things like non-termination. Erasure also helps the new type optimization, makes it more broadly applicable, and in combination with it, it can collapse large, richly indexed structures into just the bare bones representation, the meat of the structure. Finally, the identity optimization gets more powerful with erasure because it's much easier to spot that something is an identity after it's been erased. So weaken E is more obviously an identity than weaken. Finally, here are some benchmarks of my prototype implementation. The times shown include the whole compiler pipeline from parsing up to and including native code generation. And we can see that with erasure enabled, the total compilation time is much shorter because there's less code to generate. Given that we've shown that we can distinguish between compile time only information and runtime information automatically, we have shown that the commonly claimed lack of phase distinction in dependently typed programs is a myth. And it's true that the phase distinction no longer lines up with the distinction between terms and types, between implicit and explicit, but it's there and we can make use of it. So the main direction of further research is unification with QTT, which is Bob Atkey's extension of Conor McBride's work, featuring linearity as an additional quantity to erased and not erased. It would be nice to have erasure polymorphism or quantity polymorphism so that functions like apply can take erased and not erased functions. Finally, erasure can be inferred from a completely unannotated program. However, this has the same drawbacks as Haskell or an ML program without type annotations. You make a mistake somewhere, the system infers the wrong type, and then something very far away breaks, and it's hard to find the real cause. Moreover, explicit annotation would help with separate compilation, so it would be good to find a convenient rules for explicit annotation that would help with both. Thank you for your attention. Questions are very welcome.
Thank you, Matthews. If you are watching this talk live, please don't forget about a Q&A session that may be available in your time band.